All right, remember the purpose here is for you to take the logarithm of both sides in these types of equations at some point, which will allow you at some point to remove the exponents or to put the exponents out in front. Do me a favor, take a look at your work, please. I'm going to give you a minute to do so, and then I'll ask if you have any questions. Okay. Does anybody have any questions you'd like me to go over, either from the handout or the text? Go ahead, Jason. 2e? Okay. So we have 4 multiplied by 3 raised to the x minus 4. I've just rewritten that slightly different. Rather than putting the 3 in brackets, I put the whole 3 to the x minus 4 in brackets because I want to impress on you that what we have here, everybody, is a product of two things. One of the things is a number, one of the things is an exponential expression. And this is equal to 7 raised to the x. There's a couple of options here, and I want to explore them with you. Even if you got this question, it doesn't matter. Some of you might at this point do what I would do, which would be to take the logarithm of both sides. And you're going to have the log of 4 multiplied by 3 to the x minus 4 equals the log of 7 raised to the x. And then because this argument for the first logarithm on the left is a product, we're going to rewrite that single logarithm as a sum of logarithms and have log of 4 plus log of 3 to the x minus 4 equals log of 7 to the x. And of course I could have brought that x that's on the 7 down in front right here, but I didn't. So some of you might choose to do that. On the other hand, some of you might choose to do the following, and I just want to point out that what I'm going to show you will work anyway. What some of you might decide to do is before you get started taking logarithms of both sides, you might say, well, I'm going to divide both sides by 4 to clean that 4 out of there. And that's okay. It's not really a problem, but the thing that you should notice is that when you get rid of that 4 on the left-hand side, you're stuck with it on the right-hand side, right? So you can't really get rid of the 4. But if I take the logarithm of both sides now, I'm going to have the logarithm of 3 to the x minus 4 equals the logarithm of 7 to the x over 4. And when I rewrite the right-hand side now, since it's a quotient, I'm going to use the quotient rule, which means I can write it as a log of 7 to the x minus the log of 4. And this is equal to the log of 3 to the x minus 4. And that's what would happen if you took that and divided by 4 first. You would get what's on the right-hand screen. If you don't divide by 4 first, you get what's on the left-hand screen. But I hope you can see that these two things are equivalent. You know, we could just subtract the log 4. Anyway, I'm going to go with the initial thing that we did. And we have to now expand, we have to bring these exponents down in front, all of the logarithmic exponents, which is going to give us log of 4 plus, since that exponent is a binomial, we need to write it in brackets. X minus 4 quantity times log of 3 equals x times log of 7. And what you're going to eventually have to do here, everybody, is move all of the terms that have x to one side, but not until you multiply this through. You have to multiply that by 4, and you have to multiply that by x, and get log of 4 plus x log 3 minus 4 log 3 equals x log 7, and then you target the terms that have x and move them to one side. Now, and the numbers to the other side. We haven't really encountered this yet, so I think we might here. We could write this as x log 7 minus x log 3 equals log 4 minus 4 log 3. So what I've done is I've said we can move the x's to one side. Okay. So this is where we're at. You really should not take your phone out, even though I was pausing here, you guys. Now what you would do is you would factor the x out here and get x times log 7 minus log 3 equals log 4 minus log 3, minus 4 log 3 rather. And then we're done because we can divide both sides by whatever we're multiplying x by. So we're going to get log 4 minus 4 log 3 over log 7 minus log 3. Yeah.
I was just wondering, are we allowed to write log 80, log 81?
Sure. Sure, definitely. You can bring that 4 up and write that 4 log 3 as log of 3 to the 4, which is log of 81. And if it's possible for you to bring them together as a single logarithm, say on the top, as long as you don't get some fractions, which you would here, this top would be log of 4 over 81. We don't want that. Okay, but yes, you can do that. Now, my point when I was trying to clone this page is that if you were to move everything to opposite sides, so let's say that what you decided to do is move the x's to the other side, you would get x log 3 minus x log 7 equals 4 log 3 minus log 4. And you will notice, I know it's kind of tiny up top, but this line has all the same terms as this line, but they're all opposite. Everything is opposite because I've decided to move things to the other side. And the fact that I did that is, and I'm even having this conversation with you, is because it doesn't matter in this case which side you move the x's to, you're going to end up with 2 positives and 2 negatives somewhere. And the golden rule is kind of to minimize the negatives. If I factor out the x out of the left-hand side, I'm going to be left with, in brackets, I'm going to be left with log of 3 minus log of 7, which would mean that x is going to be equal to this 4 log 3 minus log 4 over log of 3 minus log of 7. And if you compare that to the answer up top, when we moved the x's to the right side, it's the same thing except every term on the top is negative and every term on the bottom is negative. And I'm pointing that out to you because sometimes you will do a question like this. You will get this answer here, and then maybe it's a multiple choice question and you look down and it's not there. Well, you need to recognize if you multiplied your answer by -1 over -1, which is equivalent to 1, everything's going to flip and become the answer that you see in the multiple choice. Okay. Any other questions before we get started today? All right. So we have one more topic to cover. As I said, I think yesterday, we are going to be reviewing for 3 days. We're going to review tomorrow, Friday, and Monday, and your exam is Tuesday. So this is textbook section 8.4, logarithmic and exponential equations, but it's the second part where we're going to be solving logarithmic equations. And we have to check for extraneous roots. And the general idea behind an extraneous root, remember a root is a solution, is that you apply all of the rules of math properly, you don't make any mistakes, but you get a number which does not satisfy the original equation. That means when you put that number into the original equation, it doesn't work. Now, extraneous roots can come up for a number of reasons. When you solve radical equations, they come up because when you square both sides of an equation, you eliminate positive and negative solutions of roots. You actually, I shouldn't say that, you don't eliminate them, you introduce them, because you maybe create a quadratic equation that has positive and negative solutions, even though that quadratic nature didn't exist in the radical equation. I'll tell you right now, the reason why an extraneous root will happen here is because the argument of the logarithm is not positive. So, for example, if I had an equation that had log of x plus 2 in it, and then there's other stuff. There could be other stuff everywhere. But in the original equation, x plus 2 is there, and you do something to this equation to solve it, and you get the following solutions. You get those two solutions for some reason. Well, the reason is that you followed the algebra, and that's where it led you. One of those is not a valid solution. The one that's not a valid solution is -4, because when you put -4 in for x, this argument becomes -2, and you cannot take the logarithm of a negative number, or 0, by the way. But so that would be stricken or tossed over the boards, or whatever you want to say. That's an extraneous root, but the -1 would work, because when you put -1 in for x, you're going to end up getting, are you with us, JB? Okay, you're going to end up getting, when you put -1 in for x, -1 plus 2 for the argument, which is 1. You're allowed to take the logarithm of 1. And that's the only way you're going to get an extraneous root. So we start off with some very basic logarithmic equations. If just think about this. If log base 6 of 2x minus 1 equals log base 6 of 11, then 2x minus 1 has to equal 11. This is very similar when we were solving exponential equations to you doing some work and getting 3 to the 2x minus 5 equals 3 to the 7, and saying since the bases are the same, the exponents must be the same. And this is going to be one of our strategies in solving a logarithmic equation. Rather than saying, can we get the same base with an exponential equation and then just say the arguments are equal, the arguments being the exponents, can we get the same base with a logarithmic equation? And if we can, then the two arguments must be equal. The only way log base 6 of a thing can equal log base 6 of a thing is if those two things are the same. So now you're solving something that, we're in stealing candy from a baby territory. As he writes down the wrong number, add 1 to both sides and you get 2x equals 12. Divide both sides by 2 and you get x equals 6. Now, is 6 a solution? When you check for an extraneous root, the general idea is you want to put it in and see if the equation is true. And if I put 6 in for x on the left side, I get log base 6 of 2 times 6 minus 1. 2 times 6 minus 1 is 11. So I get log base 6 of 11, so it's equal. What I'm telling you, though, is as soon as you put 6 in here and you see that this is going to be a positive number, you don't have to check any further. As soon as you're aware that it's a positive value, it's going to be correct. So how do we go about solving b? We can only drop the logarithms if we have log base b of a thing equals a single log base b of a thing. It will only work if it's a single log equals a single log. And if this is true, then this equals that. So this and that are not in fact different things. They're equal to each other. They're the same thing. So we're simply going to combine these two logarithms on the left and write log base 7 of 4x, because the sum of logarithms is the product, is a single logarithm where the argument is the product of the old arguments. This is equal to log base 7 of 12. Don't really need the brackets around the 12, which means 4x equals 12, which means x equals 3. Now, if you look at the argument of the logarithm in terms of x in this equation, the argument is x, and we got x equals 3. So you're going to end up taking the logarithm of a positive number, which means this is correct, just like this one was correct. C. Now C is different. One of the strategies you want to try to do is set a log equal a log. But if there is no log, what you want to do is set a log equal to something else. And if you can set a log, a single logarithm equal to a number, then you can write this in exponential form. What I'm telling you is, if part of the equation doesn't have a logarithm, then you're going to isolate the single logarithm and rewrite it in exponential form. If I rewrite this in exponential form, the base of the logarithm, which is 2, raised to what the logarithm is equal to x plus 3 quantity squared, which is the argument. And we can simplify this. 2 raised to the 4 is 2 times 2 times 2 times 2. Don't forget that x plus 3 quantity squared means x plus 3 multiplied by x plus 3. So I think most of us don't need to write that down, but make sure you're aware that that's what's going on. When you FOIL that out, you get x squared plus 3x plus 9. Now we're kind of in a Math 20-1 territory. We see that it's quadratic, which means I'm going to zero the equation and get x squared plus 6x minus 7. Help me out here. Okay. Don't forget your equals 0. This is factorable. Two numbers that multiply to give negative 7 and add to give positive 6 would be 7 and negative 1. I'll be honest with you, I don't think I've ever seen in Math 30-1 any logarithmic equation that turns into a quadratic equation where you'd have to use the quadratic formula. They're always factorable. That being said, I don't know, anything's possible on a diploma exam. We end up with two solutions here, x equals 1 and x equals negative 7, because you're really solving x minus 1 equals 0, and you're really solving x plus 7 equals 0. And now you need to do a little bit of exploring. So let's talk about x equals 1. We go to the top. If I were to put 1 in, will the argument be positive? Definitely. If I were to put negative 7 in, will the argument be positive? Yes, because it's squared, because it's x plus 3 squared. So you put negative 7 plus 3 is negative 4, squared is positive 16. Can I ask you a question? Is there a value of x that would not be allowed in that logarithm? Ben? Negative 3 would not be allowed. It isn't just that the argument has to be positive. Well, it is that the argument has to be positive. What that means is that the argument cannot be negative, but the argument as well cannot be 0. And if you put negative 3 in for x, you would get 0 squared, which is 0. Anyway, both of these survive the extraneous root check, so they're not extraneous, they're actual solutions. So now we get to a situation where we have a mixture of logarithms and a non-logarithm. Remember what I've told you, and I'll repeat it. If you have part of the equation that is not a logarithm, your approach has to be to rewrite the equation Doesn't matter what I call these. If you have part of the equation that's not a logarithm, then your goal is to rewrite it as a single logarithm equals everything else. If you have everything being logarithms, then your goal is to get a logarithm equal to a logarithm so you can drop the logs. When we get it to this stage, you're going to then rewrite it in exponential form. So in this question, I can collect the logs on both sides of on one side of the equation. So log of 8x plus 4 minus log of x plus 1 is equal to 1. And we end up with a single logarithm where the argument is 8x plus 4 over x plus 1 equals 1. And now we're going to rewrite it in exponential form. And I'll tell you right now, a very common mistake is to write the following. That's not correct. And I think why people write that is they don't see the base, so they don't think about the base. Log without a base is the common log, which is base 10, which means the argument is not equal to 1, it's equal to 10 raised to the 1. Don't forget that base. We can solve this equation now. It's a rational equation, it turns out, but I'm going to just erase something and write this a little bit differently. We have equals 10 to the 1 over 1, so this qualifies for cross multiplication. In a more general sense, what we're going to do is multiply both sides of the equation by that denominator to eliminate that denominator. And what you're going to end up with is, when I multiply this side by x plus 1, and when you multiply this side by x plus 1, you eliminate the denominators and you get 8x plus 4 equals 10 times x plus 1. And again, we're into a very comfortable territory here in terms of solving that equation. The x plus 1s cancel on the left, nothing cancels on the right. Expanding this out, you get 8x plus 4 equals 10x plus 10. Then it's a matter of solving for x. I would subtract 8 from both sides to get 2x. On one side, I would subtract 10 from the other side, from both sides to get negative 6. So I'm getting x equals negative 3. You're getting the same number? Okay, so is that an actual solution? Well, we have to go up and ask ourselves, if I use negative 3, would any of these arguments be not positive? Meaning, do I get 0 or negative? And the answer is both of the arguments are negative, aren't they? Which means that this is not a valid solution. And I really hate the idea. This causes confusion in 20-1 where you're told, well, what this is the extraneous solution. I don't even like that phrase because it's not a solution. Unfortunately, we do have to call it an extraneous root. But the bottom line is we toss it over the boards. We eliminate it. It's not a solution. What does that mean? It means there's no number in the universe that's going to make that equation true. It's impossible. Another one where we have two logarithms and a non-logarithm, so we collect the logarithms on one side and non-logarithms on the other, and I get log base 2 of x minus 6 plus log base 2 of x minus 4 equals 3. Again, I can't unpack this into an equation that's solvable until I have a single log equals a non-log. I know I'm getting boringly repetitive, but you have to get a single log equals a single log and then drop the logs, or you have to get a single log equals a non-log and rewrite it in exponential form. I can put this as a single logarithm of the product of the arguments, which will give me log base 2 of whatever the product of x minus 6 times x minus 4 is. This will equal 3. And now I can rewrite this in exponential form. the argument of x minus 6 times x minus 4 is going to be equal to 2 raised to the 3. That 2 and 3 thing, be very careful. I know a lot of people look at this and they go, oh, it's 9. It's 8. 2 raised to the 3 is 2 times 2 times 2. 3 raised to the 2 is 9. So I'm going to do 2 steps at once here. I recognize that this will be quadratic because if I FOIL this out, I would get x squared. Can somebody tell me what the problem with this is, though? And I have seen this. I've seen students stop at this point on an exam and go, oh. X equals 6 and x equals 4. What's the problem with that person's reasoning, Evan? Right, the equation isn't zeroed. It's not equal to 0. That only works when it's equal to 0 because what you're really doing is you're saying each factor then has to be 0. But if it's equal to 8, that's not going to work. So you do need to FOIL this out, multiply this out. In my case, what I did was I filed it out instead of FOILed. I went first, inner, outer, last. Doesn't really matter the order. And then we can subtract that 8. This is 8. And this is the equation you're left with trying to solve, which is in even more simplified form. X squared minus 10x plus, help, 16? Thank you. Well, that factors into x minus, 2 numbers that multiply to give 16 and add to give negative 10 would be negative 2 and negative 8. Now don't forget, when I say the numbers are negative 2 and negative 8, those are not the solutions. Those are the numbers that appear in the binomial factors of that trinomial. So we get x equals 8 when we set x minus 8 equals to 0, and we get x equals 2 when we set x minus 2 equals 0. Take a quick look up here. If x is 8, 8 minus 6 is a positive number. 8 minus 4 is a positive number. We don't need to go any further. Since 8 results in all positive logarithms, my mistake, since 8 results in all positive arguments of the logarithms, 8 is a solution. The other one was 2. 2 is not going to work because 2 minus 6 will give you a negative. And by the way, once again, I don't know if I said this the last time. The arguments don't have to be not positive everywhere. If you get an argument somewhere in the equation that's negative or somewhere in the equation that's 0, it doesn't matter what the other arguments are. They could be defined. Those logarithms could work. But if one is not defined, the whole thing is not defined. So 2 is not a solution. Any questions with that one? All right. Log base 3 of x squared minus 8x raised to the 5. The intention here, everybody, is this is log base 3 of x squared minus 8x raised to the 5 as a quantity. This is equal to 10. Now, I'm going to write something down that I don't want you to write down because I'm going to erase it. You could write it down and then put a big no beside it. But if you were to write this in exponential form, you're going to get x squared minus 8x raised to the 5 equals 3 to the 10. I'm missing an x here. You're going to get this equivalent exponential equation. Now, I don't know what 3 to the 10 is. I suspect it's in the tens of thousands. But I do know that the only way for you to solve this equation is to expand out x squared minus 8x to the 5. Let me write that down for you to look at. You would have to take this thing and multiply it by itself 5 times, which would give you a degree 10 polynomial expression. Now, Liam, have you calculated what 3 to the 10 is? 59,049. Now, this thing that you're looking at up here is equal to 3 to the 10, which is this number that I've written in red. And that means that this equation is going to be a polynomial equation where you now subtract 59,049, set it equal to 0. Think about this. Expand it all out to get a degree 10 polynomial function and then try to factor it using synthetic division and the factor theorem. So you're going to be looking at numbers that are factors of 59049. You're going to be doing synthetic division with at least 10 columns at one stage, 11 columns because you also have the constant number. It's going to be a nightmare. So what we do in this case instead is we bring that 5 down in front. We don't want to do that. We bring this 5 down in front and have 5 log base 3 of x squared minus 8x equals 10. Then divide both sides by 5, and now we've whittled it down to a more manageable equation. When I divide both sides by 5, I'm going to get log base 3 of x squared minus 8x equals 2. All right, I'm liking the looks of this now, because now if I put this into exponential form, I end up with x squared minus 8x. The argument is equal to the base of the logarithm raised to what the logarithm is equal to, which is the exponent. Keep missing my x there, I apologize. So we have x squared minus 8x equals 9. Zero that equation. Get x squared minus 8x minus 9 equals 0. Factor it. Negative 9 times 1 is negative 9. Negative 9 plus 1 is negative 8. What do we discover after all of this? That x equals 9 or x equals negative 1? Well, maybe. We have to go back up and check to make sure the arguments are valid arguments for logarithms. Now, we've got to be careful here, because the argument is a power that has an exponent of 5. So in one of these questions, we had it squared, and I said, well, it doesn't matter what the argument is as long as it's not 0. When you square it, it will be positive. We've got to be careful here. If I put 9 in, was 9 one of the solutions? I'll have 9 squared minus 8 times 9. I think that's 9, which is a positive number. A positive number raised to an odd exponent like 5 will give you a positive result, which means 9 is okay. What do I get if I put negative 1 in? Well, negative 1 squared is positive 1. Minus 8 times negative 1, I also get a positive number. Because minus 8 times negative 1 is the same as plus 8 times positive 1. So both of these are valid. All right. Let's take a look at something more challenging now. And, I know that what we've just been doing is challenging, but this is even more challenging. What we have here is a logarithmic equation that's quadratic in nature. And I don't mean it turns into a quadratic equation. This is the same as, well, let me rewrite it first. No. Let me make sure you understand something here. That in log base 2 of x that's in brackets squared, this whole thing is squared. This means log base 2 of x times log base 2 of x. In log base 2 of x squared, even though the brackets aren't there, it's implied that the squared is on the x alone. So in this, and I'm only doing it this way for somebody watching the video, that exponent of 2 is part of the argument, which means we are allowed to move it out in front. But in log base 2 of x quantity squared, which is this, that exponent is not on the argument. We cannot move it in front. What happens when we move that exponent in front that we are allowed to is we get log base 2 of x quantity squared minus 2 log base 2 of x equals 0. And this is no different in principle than solving this equation. It's something squared minus 2 times that thing equals 0. And if you solve this equation, you would factor out the a, and you would get a equals 0 for this factor, and you would get a minus 2. You would get a minus 2 equals 0 for the second factor. It's no different than having sine squared of x minus 2 sine of x equals 0. Right? No, you don't have to write this down that's on the side. If you are, that's great. But this is the same kind of thing. You would factor a sine of x out and be left with sine of x minus 2. You would then say that sine of x equals 0. You would say that sine of x minus 2 equals 0. This second equation would become sine of x equals 2. Now, I want to point something out to you. That if you were solving the equation in red, when you get to this point right here, and you write a equals 0 and a equals 2, you're done. That's where the problem would end. You've solved for a. If you had a trigonometric equation that was quadratic, when you get to this point, here and here, you're not done. You have more work to do to find x, right? You've got to unravel the signs, or the trig in general. So how do we transfer that kind of strategy to this? We say there's a common factor of log base 2 of x here. And if I factor log base 2 of x out of log base 2 of x, quantity squared, I'm left with log base 2 of x. Just like when I factor a out of a squared, I'm left with a. When I factor log base 2 of x out of negative 2 log base 2 of x, I'm left with 2. Just like when I factor a out of 2a, I'm left with 2. And it's negative. So now I can say log base 2 of x equals 0, and log base 2 of x minus 2 equals 0, which becomes log base 2 of x equals 2. But I'm not done. This is very similar to solving the equation in green, where I said when you get to here, you're not done. You still have new equations to solve. How do I solve log base 2 of x equals 0? I write it in exponential form, because it's a logarithm equals a non-logarithm. X equals 2 to the 0, which means x equals 1. How do I solve log base 2 of x equals 2? And again, everybody, if you just look up here, I just cast my eyes up here and looked at what I wrote. It's not wrong, but I can see how somebody might look at that and think it's the logarithm of x minus 2. It's not, right? It's the logarithm of x, which is why these brackets are maybe a good thing to always have, and then minus 2. Anyway, when we write this in exponential form, you get x equals 2 to the 2. 2 to the 2 is 4. So our two solutions are x equals 1 and x equals 4. Do they work? Well, they're both positive numbers. So log base 2 of x is defined, and log base 2 of x squared will certainly be defined, because when you square x that's already positive, it will be positive. They're both solutions. How many of you see that this is a quadratic equation as well? You may not see it until you rewrite this log of x quantity squared. By the way, I wish, I want to start a campaign, but I don't have enough followers for this to take root. I wish somebody would adopt this as a strategy. Just like we do with trig, right? Sine squared of x. Why don't we write log squared of x? But apparently we don't. I don't know why. I think it would be a really good move. Let's rewrite this as log of x quantity squared minus 5 log of x minus 24 equals 0. I hope it becomes clearer that this is quadratic. The first term has an a value of 1 times a thing squared. The second term is the linear term instead of the quadratic. It has a coefficient, a b value of negative 5 times that quantity to the 1, and then the constant term. So when we factor this, you're going to factor it into log x. Well, you're going to factor it into two binomials where the first term of each binomial is log of x. And you've got to have two numbers that multiply to give negative 24 and add to give negative 5, being negative 8 and 3. That's going to mean log of x equals 8, but I'm going to actually write log of x minus 8 is equal to 0. And I'm going to write log of x minus or plus 3 equals 0. When I rearrange this, I get log of x equals 8. And I rearrange this and get log of x equals negative 3. Now what? Ryan?
You convert it to exponential form?
What's the base?
10.
Right. I convert it to exponential form, remembering, of course, that it's base 10 because the base is not specified, which means it's the common log. It's so common, we use it all the time. We don't need to tell you it's 10. You're expected to know it's 10. And that means we get x equals 10 raised to the 8th. I don't think we need to write out 100 million. You could write 1, 0, 0, 0, 0, 0, 0, 0, 0. We also get x equals 10 to the negative 3, which I'm more comfortable writing it as 1 over 10 to the positive 3, but I don't care. These are both positive numbers, though. Now, you want to be careful here, everybody. Just because you get a positive solution doesn't mean it can't be extraneous. Because maybe when you put that positive number in for x, the argument becomes negative. Because maybe the argument is 1 minus x. And when you subtract x from 1, you get a negative. Maybe. It's not in this case, because I believe our arguments here were all just x in the first part, and x to the 5 in the second part, but if x is positive, x to the 5 will be positive. So these are both valid solutions. 100 million and 1 over 1,000. And I'll be honest with you, this is like your math teacher. You come in and sit down, your math teacher picks up a sharp stick and starts poking you. This is a really weird question to wrap your head around. But I don't want to say it's beyond the scope of a diploma exam. And again, my job here is not just to prep you for the diploma exam, but to prep you for next year and for calculus, for those of you taking calculus. So we got to get at x. We got all kinds of stuff crowding around x that we have to peel off. And when you take a look, listen very carefully to this. I'm not going to write it down, but what happens to x is the first thing you do is you take the cosine of it. The second thing you do is you take the base 2 logarithm of it. The third thing you do is you multiply it by 4. And the last thing that's done is 2 is added. And I've used this analogy in 20-1 with you. When you solve an equation, it's like unwrapping the equation. It's like unwrapping a present in a civilized manner. If the very last thing I do in wrapping your present is putting the bow on it, then you're going to take that bow off first. So I put the bow on last, you take the bow off first. If I add 2 last, the first thing you're going to do is subtract 2. The one thing I did before I added 2 was I multiplied by 4. So working backwards, after we subtract 2, we're going to divide by 4. We get 4 log base 2 of cosine of x is equal to negative 2, which means when we divide both sides by 4, I get log base 2 of the cosine of x is equal to negative 2 over 4, which we can simplify to negative 1/2. I rewrite this in exponential form and get 2 raised to the negative 1/2 equals cosine of x. What does 2 raised to the negative 1/2 mean? It means 1 over 2 to the half. This is equal to cosine of x. Well, 2 to the half is root 2, so we have 1 over root 2 equals cosine of x, which I'm a unit circle person, and I'm forcing you to be. We're not learning logarithms in isolation of everything else. We've talked about polynomial functions today, quadratic functions. Well, there's trig. On the unit circle, cosine is the x-coordinate. I hope I just said cosine is the x-coordinate. Is that what came out of my mouth? Better be. The x-coordinate is 1 over root 2 at these 45-degree increments. Right here, this is 1 over root 2. This is 1 over root 2. So is the y-coordinate, 1 over root 2 and negative 1 over root 2. But I really don't care about that. I'm interested in the x-coordinate, which means x is pi over 4. X is also 5 pi over 4. And there's nothing in this question that said it has to be between 0 and 2 pi. It can be any angle that has that same position. So for both of these, we can put plus multiples of 2 pi. Well, you know what I mean by multiples. I mean n is an integer. Some people at this point will go, but wait a minute. What if x is negative? Like, negative pi over 4 is included in what I've just written here, which is the solution. So x is negative. But when you go to the equation has an argument of the cosine of x. And the cosine of negative pi over 4 is 1 over root 2. It's a positive thing. Any questions with that one? It's a pretty deep question because it involves, rearranging kind of a linear thing. It involves logs and trig. Go ahead. Pardon me? Thank you, Zebby. It should be 7 pi over 4. Absolutely. Thank you for catching that. 5 pi over 4 is over here. My mistake. I'll mark off the pi over 4s just because I made a mistake. I don't want to cause any confusion here. This is 0, so this is 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4. This is, in fact, 7 pi over 4. My mistake. I hope Zebby was not the only person that caught that. Anybody else catch that? couple maybe. Just a reminder to be, not just to see if you can catch my mistakes, but a reminder to be an active learner. Don't just sit there and copy. Think about what's going on. Any other questions with that example? Okay. So in your handout, there are a variety of questions. Is this what I have typed up at the bottom of page 21 on your handout?
No, it just says number 20.
So it doesn't have the 21. I took that out. I'm not sure what the deal with number 21 is. You could probably try it. I think it's probably very challenging, whatever it is. I'll maybe take a look and we can address it. You have about 25 minutes here to work on these problems. These are all about logarithmic equations. All of these logarithmic equations here are kind of polynomial logarithmic equations, either quadratic or cubic. So multiple choice, you get the idea.